Okay, we are going to talk about 4 theorems. I'm looking at this page of your notes, so open your page, your note packet to this page of notes. We're going to look at these 4 theorems. The first one has 2 chords intersecting inside a circle, or it might be 2 secant lines intersecting inside the circle. Okay, so if we stop them here and here, they're chords, but if we continue, they're secant lines. They're intersecting inside the circle at this point right here. All right, so what we're going to do is we're going to talk about a relationship between the angles at that intersection point and the arcs on the circle, the degree measures of these. Now, what my theorem says is if I want to find the measure of angle 1, let's just analyze this. It says take arc AD, which is this arc right here. Take the degree measure of that arc, add the degree measure of this arc that's created by the vertical angle for angle 1. And if I take that sum, let me call that x and y. If I take x and y and divide by 2, I have the measure of angle 1. Okay? We can do a similar thing for angle 2. So look at what this one says. Angle 2 is right here. If I take the measure of arc AB, add the measure of arc CD, here it is, and I divide by 2. Remember, multiplying by a half is the same as dividing by 2. So angle 2 is equal to, let me call these W and Z. If I take W plus Z and I divide by 2, I have the measure of angle 2. So there's a relationship between the angles and the arcs when I have intersecting chords. Second theorem, right here. So this is the second theorem. First theorem, second theorem. Maybe you number them. So if we refer back to them, this is theorem 1. Theorem 2. 2 chords intersect inside a circle, then the product of the lengths. Remember, product means multiply. The product of the lengths of the segments on one is equal to the product of the lengths of the segments on the other. So what I'm going to do is I'm going to come over here and I'm going to look at this diagram. So it says AE, that's this length right here, times EB, that's this length right here. So if I multiply the 2 pieces of the one chord, that has to be equal to, there's DE, the product of the 2 pieces on the other chord. Okay? And we'll look at some examples in a little bit, but that's what we're looking at. All right? Theorem 3. Here's theorem 3. If a line is tangent to a circle, then it's perpendicular to the radius drawn to the point of tangency. Well, let's look at the diagram over here. This is the second time we've seen this theorem. I have a tangent line right here, okay? Tangent L. Point of tangency is point P right there. That's called the point of tangency. Point of tangency. The radius right here, there it is, CP is a radius. The radius is perpendicular. Notice that 90-degree angle there. The radius is perpendicular to the tangent line at the point of tangency. So we have a 90-degree angle, 2 90-degree angles right there. Okay, the final theorem. If 2 segments from the same point outside a circle are tangent to the circle, then they are congruent. Remember, congruent means equal. When we're talking about line segments, they're equal length. So over here, I have a picture. We have a circle with its center at point B. That's this notation right here. It says LM. Notice the single arrow right there. So we start at L and we go forever in the direction past M. All right? LM is tangent at the point M. So point M is right here. Point N is right there. And LN is tangent at N. What that says, what the theorem says is this length right here and this length right here are the same. So I could put little marks like that. They are the same. 2 points, or not 2 points, 2 tangents from the same point outside the circle. Those segments are the same length. Okay, let's look at our notes, and then we'll do one extra example. So in our notes, so flip to the next page, properties of chords and tangents. We're going to talk about example 1 right here, the vocabulary. So in the diagram, AC is tangent to the circle, and that circle has its center point at O. Point B is where AC intersects the circle O. All right, so there's point B is the point of tangency, point of tangency. Let's make sure we know how to spell that. Tangency, point of tangency. AC is, how is AC related to radius OB? Oh, they're perpendicular. The radius is perpendicular to that tangent line, tangent segment. Okay? Notation for perpendicular. I need you to be familiar with this. That symbol means perpendicular. AC is perpendicular to OB. All right? And then we have, how big is angle ABO? That's what this is asking. What's the degree measure of angle ABO? Well, let's look at ABO. ABO is right here. Oh, ABO is 90 degrees. That's my right angle because AC is perpendicular to OB. Now, the final piece of this little puzzle. Where is the X in the picture? X is right here. So X is an angle. How big is angle X? Well, the 28 and the X have to add up to 90. So X is 90 minus 28. X is 62 degrees. And we will move on to the second example over here. Example 2, right there. Okay. For the figure at the right, find the measure of angle ABD. The first thing you're going to do is you're going to analyze the picture. Here's angle ABD. What do I have? Oh, I have some arc measures. The measure of that arc is 65. The measure of this arc is 37. I have a secant line intersecting a chord. That's okay. One can be a chord, one can be a secant line. They just need to intersect inside the circle. Notice they intersect at point B right there. Angle ABD, oh, this is the theorem that says if I want this angle, right there, angle ABD, I take the arc plus the arc and I divide by 2. So angle ABD is going to equal 65 plus 37 divided by 2. Be careful how you plug that in a calculator. You need to make sure you do the 65 plus the 37 twice. That's going to be 102. And then if I divide 102 by 2, I get 51 degrees. So angle ABD is 51 degrees. Next one, angle CBD. Where's angle CBD? C to B to D. That's this angle right here. So angle CBD, oh look, the angle that we just found and angle CBD add up to 150 degrees because this is a straight line. So if I do 180, take away 51 degrees, I have the measure of angle CBD. Yes, we have to use some of the ideas from previous sections of this unit. 129 degrees. Right? Second example in this section, the circle at the right, A, B, and C, D are chords intersecting at E. Oh, yours is a little better printed than mine. My B got a little hidden. Intersecting at point E. I like to have the labels on my picture, so I'm going to put the labels on the picture. AE is 5. That's this segment right here. BE is 9. That's this segment right here. CE is 8. That's this segment right here. And I'm supposed to find DE. Well, look, this is the theorem that says if I multiply, I'll call that one X. If I multiply the pieces of one segment, so if I do the 8 times the X, the pieces on one chord, I should say, the pieces on the one chord, the chord CD, the product of those pieces should equal the product of the pieces on the other chord. So the other chord AB has segments that are 5 and 9. So if I multiply 5 and 9, I get 45. Divide by 8, I get x equals 45 divided by 8. So D is 45 divided by 8. I will grab a calculator and do that. It's 5.625, and I am finished. No, they do not have to come out to whole numbers every time. Okay, example 3. So they didn't tell us it was a tangent segment, but it is a tangent segment. So this segment that has the question mark on it is a tangent segment. So that's the point of tangency right there. Okay, and I'm supposed to find this length right here. I'm going to call it x. Notice this entire length is 15. Oh, this is a 6 right there. So that means this is a 6 right there because those are both radii of the circle. So this length right here all the way across is 12. The diameter is 12. That's the diameter of the circle. It's 12. All right. Oh, because I have a segment tangent to a circle, there's a 90-degree angle there. That radius and that tangent segment make a 90-degree angle. So I can use the Pythagorean theorem. So to solve for the missing side x, I'm just going to solve x squared plus 12 squared equals 15 squared, because this is the hypotenuse of my right triangle because it's across from the 90-degree angle. Okay, so solve the equation. X squared plus 12 squared equals 15 squared. That's a 12 squared. Okay, so x squared plus 144 equals 225. Subtract 144 from both sides. 225 minus 144 is 81. Square root both sides, we get x equals 9. X is a length, so it needs to be a positive number. Right? Pythagorean theorem. It's a big tool. All right, so in this picture over here, for example 4, this last example, example 4, it didn't say they were tangent segments, but they are. So I'm going to tell you they're tangent segments. In the homework, I tried to tell you when things were tangent. I think most of the time we say if it looks like it's a tangent, it is a tangent. All right, so this is a plus sign. If your notes don't look super clear, make sure you write it up above there. That's 2x plus 12. That is a plus sign. Let's see, I have two tangent segments. Oh, Theorem 4, our last of the theorem, says if I have a point outside the circle and I have two tangent segments, then these lengths are the same. So I will solve the equation 4x minus 8 equals 2x plus 12. That will get me the value of x that I'm looking for. So let's solve that equation. I'm going to subtract a 2x from both sides to get the x's on the same side. I will have 2x minus 8 equals 12. I will add 8 to both sides to get 2x equals 20. I will divide both sides by 2, and I will have x equals 10. And we are done. End of video. Oh, nope, there's one more example. Here we go. One more example, because not all of your problems are going to be exactly the same. You might have to think about it and plug some numbers into a formula a little different way. So in this example, we have a circle and we have two intersecting chords. They intersect inside the circle. Here's the intersection point inside the circle. We're looking for the value of x. X is the degree measure of arc BD. Okay. Now, I think my 138 is the wrong place. This angle right here is going to equal 72 plus x divided by 2. But if I can find this angle, let me call this one maybe y. If I find angle y, that missing angle right there, I can subtract it from 180. Whoa, wait, what am I saying? Rewind. I know what that angle is. How do I know that angle? Oh, these two angles, it must be getting late. It kind of is. these two angles right here add to 180 because that's a straight line. So if I want to find that angle, I subtract 138 from 180. And that angle right there is 42 degrees. Okay, oh, now this is going to work out well because 42 has to equal 72 plus x divided by 2. That'll get me an equation I can solve for x. 72 plus x, or x plus 72, same thing, divided by 2 equals 42 degrees. So to solve this, I can do it several different ways. I could put that 42 over 1 and then cross multiply, or I could just multiply both sides by 2, because to undo divide by 2, I multiply by 2. So I'm going to do that. I'm going to multiply both sides by 2. 72 plus x equals 84. Okay. Subtract 72 from both sides, and we get x equals 12, and we are finished. I don't think that was drawn very well to scale because it looks a lot bigger than 12 degrees, but we're going to go with it. X equals 12. We're done.